Hello, everyone. Here's the microphone. Hello, everyone. This lecture has quite a bit of math in it, and it doesn't make sense for me to narrate the math. So I thought what I'd do here is give an overview and let you read the slides at your own pace. So there are three sections in here. The first is deriving the maximum likelihood estimator of beta and sigma. And in this section, it turns out that the maximum likelihood estimator of beta in linear regression is actually least squares. That does not generalize to other types of regression in the generalized linear model framework. Linear regression is one member of the generalized linear model. But here it holds. So that's quite interesting that two approaches come up with the same answer. Now, for sigma, maximum likelihood estimation leads to a certain formula, and the sample variance or the unbiased estimator of sigma that we know from introductory courses leads to a slightly different answer. The difference is in, do you divide by n to take the average, or do you divide by n minus the degrees of freedom, which is needed to make the estimator unbiased. And so there are these two estimators, and it turns out that software uses the unbiased, the sample variance estimator, not the maximum likelihood estimator. And that is already the second section, which estimator of sigma does the software use. And then there are a number of properties, and I'm going to skip ahead now. It's going to be a little funny now as I'm scrolling ahead and talk about them in a slightly more detail. So that was the software use. Here, I think here we are. Here. So the linear regression model has several assumptions. One, of course, is that the model is linear. You can see that here because this is a linear construct, right? And I guess you could add that the error is additive rather than multiplicative or something else. Then the residuals, the error is normally distributed. So I have a G here for Gaussian distributed with standard deviation sigma. Now, the standard deviation here, sigma, is a constant. It does not depend on x. I don't say sigma as a function of x. I just say sigma. And that's another assumption, that we have constant variance. Whether you say standard deviation is constant, then of course sigma squared is also constant, right? The residuals are independent, identically distributed. And so independence is another assumption, identically, I guess, too, but independence is really the key thing here. So that's the assumptions. The estimators of beta under the maximum likelihood and the least squares estimate is the same, right? So if we take the expectation, we just drop the error term. If we take the variance of yi, we get sigma squared as, which is nice. Before we had assumed that the error, the variance of the error is sigma squared, variance of epsilon, and it turns out it's also the variance of y. Okay. So y's are normally distributed, and we know already the standard error is sigma, and they have the entire model is the mean. So this mean varies depending on the values of x. And so I could substitute, and instead of saying this entire formula, I could just say mu I, where mu I equals this long thing. So the yi has a mean constant error, but the mean is not constant. It depends on x. So this means that the linear regression is appropriate for y variables where the Gaussian distribution assumption fits, and that may or may not be true. All right, so this next little section is about the expected value of beta hat, where beta hat is the estimator, turns out to be beta. So the estimator is unbiased. That's beautiful. The math is here. Then this is some linear algebra that you need to go look at. The variance of the estimator of beta hat is this term here. So before we had assumed the variance of epsilon is sigma squared. We had found out that the variance of y is sigma squared, the same thing. The variance of the estimator of beta is sigma squared times something. And the sort of one way of understanding that it must be times something is if you are estimating the variance of an average, then that is sigma squared divided by n. So it's times 1 divided by n. So therefore, if I have the variance of another estimator, not necessarily average, but something more complicated, then I must also have sigma squared times something. And that something is x prime x inverse. That means, given that we know the expected value and the variance, that means that the beta, which is a vector with p plus 1 entries, because there are p variables and then there's beta 0. So the vector is multivariate normal with expected value beta and mean beta and the variance as we have shown. So this means that the betas are correlated because this variance covariance matrix, well, sigma squared times this expression, this thing is not in general a diagonal matrix. So if you can choose the x values such, you can choose them to minimize the variance, and that is a branch of statistics called experimental design. Not what we do here, but this is sort of the one starting point in experimental design. I place my axis such that the variance of the resulting estimator is very small. Yeah, that's the same thing. And the learning objectives, which are also in the slides. All right, that was the overview of this lecture, and that brings me to the end.